And you see the screen.
It's all good.
Excellent. Okay, thanks for the introduction. I'm going to present TaDA Live, which is joint work with Julian Sutherland, Azadeh Farzan, and Philippa Gardner. Do you see the screen? It looks a bit...
we can see it fine.
Yes, okay. So the goal of this work is compositional verification of total correctness for fine-grained concurrent programs with blocking behavior under fair scheduling. By total correctness, here we mean both functional correctness.
Actually, the screen is a little bit messed up.
Yeah.
Can you read it somehow, or?
Let me attempt at this. Is this better? No. 1 second.
We're somehow seeing overlapping content from different windows.
Give me 1 second. Can you see it now?
This looks good.
Okay. So the goal is compositional verification of total correctness, and by total correctness we mean both functional correctness with termination guarantees. And the approach we propose is a novel concurrent separation logic that we call TaDA Live. So to see what the problem is, let's define first the words that I just said. And let's have a look at an example. Here we have two threads. It's a concurrent program. The two threads share a memory cell at X, and the thread on the right here is repeatedly reading from the cell, waiting until the value at the cell becomes 1. And the thread on the left is setting eventually this cell to 1, practically implementing a signal between the two threads. Now, when we say fine-grained concurrency, we basically mean that the programming language is not offering primitive means of synchronization between threads, but instead the threads implement custom busy waiting patterns like the loop on the right to implement synchronization between the threads. By blocking behavior, we mean exactly what is happening in the right thread here, which is that the termination of this loop is conditional on the other threads cooperating. And finally, in this situation, when there's blocking, it's very important it's actually necessary to assume that the scheduler is fair, because in the example, for instance, if the scheduler leaves the left-hand side thread starved, then there would be no hope for the right-hand thread to terminate. So this would be the fairness of the scheduler will be an assumption that we have underlying the whole talk. We are interested in improving functional correctness with termination guarantees, but the challenge here is that we want to do it compositionally. So for instance, we want to have a thread local proof, which means that we proof each thread in isolation individually, and then we compose the proofs in a proof for the whole program. This is especially challenging when blocking is involved, because blocking introduces these dependencies between the threads. Moreover, we also want to be able to look at a fragment of code and analyze it, produce a proof towards a specification, and use the specification in larger contexts that use this code. And this is the key to have a modular logic. This is especially important if this code is actually the implementation of a library function, and we don't want to spill the insights of the language of the library for proofs of clients using the library. So in the past, separation logic has been shown to be the key to obtain these compositionality properties of proofs for partial correctness, and we want to bring this into liveness reasoning as well. So the crucial question here is, how do we design specifications that support compositional proofs? The standard specification format when one is interested in termination guarantees is total Hoare triples. They assert that the program C, running from a state satisfying the precondition, will always terminate in a state satisfying the postcondition. This is a good specification format for the overall goal of our proofs. Here, for example, I'm setting out to prove termination of this program by attempting to prove the triple where the precondition just states that the cell is initially 0 and postcondition true, but still the triple will imply termination of the program. The issue with total Hoare triples is in giving specifications for subproofs. For example, if we want to give a total Hoare triple for the loop on the right, we would not be able to state useful properties. We would, of course, be able to prove that the loop terminates when x is 1, but that's exactly a situation where the loop is completely pointless. We would like to prove properties of the code when the x is shared and can change its value between 0 and 1. But in such situation, the termination is not guaranteed, so the triple does not hold. So when there's blocking, what we would like to prove is something more subtle, which is termination conditional on the environment, setting x to 1 eventually in this instance. And more generally, we would like to state termination conditional on liveness properties of the environment. The lies of starting observation is exactly this, that blocking can be characterized by termination conditional on liveness invariants. And here by liveness invariants, we mean properties of this form. Always, eventually a good state is reached. In other words, in any point in time, there is a point in the future where a good state is observed. Now, to turn this observation into program logic, TaDA introduces 3 key innovations. The first one is subjective obligations, which are a way to do thread local and resource-based reasoning with liveness invariants. The second one is obligation layers, which are a compositional way of reasoning about deadlock freedom. And the third is logical atomicity, which is really the cornerstone of the logic and what enables modular reasoning in the logic. Now, the paper is 84 pages long. We go in all detail in the paper. We give examples and case studies. But here I want to just give you an overview of the subjective obligations idea and then touch on the other 2 very quickly. So let's see the main idea, obligations, subjective obligations in an example. Now, we can try and start with a safety proof and then see what happens if we want to prove termination. So the live is based on TaDA, which is a concurrent separation logic, which allows thread local proofs of the form that we would like to have. And the proof will start by saying, okay, you want a thread local proof, it means that you have to split the state into separate portions, 1 per thread, so that we can do the separate proofs. The first issue you have to solve is that the cell cannot be given ownership to just one of the threads or the other thread, because both need to know about the cell. So TaDA offers a way to share the cell by making up a new resource which can be duplicated and given to both threads, and we call this shared of x. So sh of x, I'm going to pronounce it as shared of x. And with it is associated a protocol that first records the fact that to affect the state of the shared x, we need to affect the value stored at x. And secondly, that there is a protocol that should be followed on this shared piece of state, which says that the value of x can go from 0 to 1, but not from 1 to 0. And that this update is only available to whoever is holding W, which is an exclusive write permission that we are going to give to the left thread here, which is the only one writing to X. If we want to add to this proof, I mean, TaDA can carry on with this proof, but it will only prove partial correctness. If we want to turn the proof into a total correctness proof, we could try apply the standard Hoare logic while rule for total specifications, which requires you to prove that there is a loop invariant P, but P is parameterized by what is called a variant, which is an upper bound on the amount of work to do, and you have to prove that after each iteration, the amount of work decreases in a well-founded order, and this proves that there will be only finally many iterations overall. The issue here is that we cannot use this rule on in the loop that we have, because there's iterations of the loop where absolutely nothing changes. So there's no way we can define an amount of work that decreases. So TaDA's while rule proposes to relax the rule by allowing the work to be done to remain constant after an iteration. But of course, this will not be enough. We also require the user to specify a set of so-called target states, which are states the environment is supposed to take you to, right? From which we can provably show that the work strictly decreases. In this case, the target state would be the states where x is 1. Again, this is not enough to conclude termination. What we additionally need to show is that the environment actually does take us eventually to t, and in a stable way. So in other words, we need to prove that eventually t is always true. So in effect, this rule reduces termination of the while, the loop, to proving this that we call environment liveness condition. Here I'm using LTL just for illustration purposes. The actual TaDA live does not require temporal reasoning, and it achieves to prove this property, something like this property, through resource-based reasoning. So now the proof is reduced termination to proving this property about the environment. The issue is that we don't have enough information in the protocol to conclude that this is true. The protocol only says what is allowed to happen to the shared resource, but not what will happen. In other words, it's only telling us safety information and not liveness information. So TaDA live adds what we call obligations to solve this problem. Obligations are tokens. Here we call it U. And they can be owned by threads, and U is called fulfilled if nobody is holding it. And implicitly, we associate with an obligation the idea that at any point in time, there will be a point in the future where U is fulfilled. So there is this liveness invariant associated with them implicitly in the semantics. We also introduced two new assertions. One is called local obligations that assert that I own the obligation U locally. And the other is called an environment obligation because it states that I know that the environment owns the obligation U. With these tools, we are able to finally prove the environment liveness condition by augmenting the protocol with liveness information. So we make up this new resource U, which is an obligation, and we instrument the protocol by saying that the transition that goes from 0 to 1 also consumes the obligation U. You go from holding it to not holding it anymore. And so we say that updates fulfills U. So given this information in the protocol, we can set up the loop invariant of the while to state that when x is 0, actually the environment owns the obligation U. Because we have this implicit invariant that says that eventually U will be fulfilled, fulfilling U, given the protocol, what the protocol says, means that x will be set to 1 eventually. And We can also add the information that is a safety information from the protocol that when it's set to 1, it cannot go to 0. So overall, we transformed the liveness invariant that says always eventually use fulfilled into eventually X is going to be always 1, which is what the while rule was asking us to prove. Now, we can package this into a proof in TaDA Live, and one crucial thing here is that these environment obligation assertions are able to, with them we are able to give a completely thread local proof here, although we need to know something about the environment and its promises. The actual TaDA Live logic, of course, has a lot more parts and mechanisms. For example, the rule of parallel composition has additional side conditions that basically here would amount to checking that the obligation on the left is actually consumed in the post condition. The while rule is also more general than I presented, and these environment liveness conditions do not require trace-based reasoning, but we have a separate judgment and proof system to discharge them. Finally, we need to also detect lead locks, and what I presented so far does not do that. But with the second innovation I mentioned earlier, the obligation layers takes care of them. We will not have time to go through obligation layers. But I do want to explain a little bit about logical atomicity for blocking code. So logical atomicity was invented in the safety case to give specifications that were precise for code that behaves as if it's atomic, although it may be implemented through a sequence of steps, which roughly corresponds to the idea of linearizability. It proved to be key in enabling modularity in the logic, so you could prove a library correct with respect to a logically atomic specification once and for all, and do proofs of clients using the specs that were proving very strong properties about the client. TaDA Live is the first logic that brings logical atomic specs for blocking code in a concurrent separation logic with a total semantics. So to see what logical atomicity is about, consider an implementation, a fine-grained implementation of a lock with its own internal data structures and busy waiting patterns. And we want to give it an abstract specification to be exposed to the clients. Consider the lock operation that acquires the lock. We could attempt at giving it a Hort triple specification like this that tries to express the fact that before calling the lock operation, the lock is unlocked, and afterwards it will be locked. The problem with this is that the precondition requires the caller to prove that the lock is stably unlocked before calling the lock, which basically implies that no concurrent access to the lock is possible, and defies the purpose of having a lock in the first place. So this is not a good specification. And TaDA proposed a specification format, which are called atomic triples, where there is this funny quantifier here that expresses the idea that the abstract state of the lock may fluctuate between 0 and 1 during interference on the lock. And the angle brackets signify that the transition from unlocked to locked happens in a single instant in time. So this proved to be good for doing modular proofs. They're precise and can be verified. The problem is adding totality to this specification, because just by knowing that the abstract state fluctuates between 0 and 1, we cannot conclude definite termination of the invocation of the lock acquisition operation. Because if the environment acquired the lock and forgot to unlock it, this local call would just hang forever. And so we cannot just say, well, the atomic triples imply termination of the operation. Instead, TaDA Live proposes to expose the liveness invariant required to guarantee termination in the specification. And here we propose this double arrow notation, which specifies what are the good states. And the associated liveness invariant is that always eventually the good states are reached. In this case, always eventually the locked lock is unlocked, and exposes this as a requirement on the client to prove. So the TaDA logic can verify fine-grained implementation against this spec, and the implementation proof can make use of the liveness invariant from the spec to establish termination as an assumption. And within the logic, we can also use the specification to verify strong specifications of clients. And the proof of the client can set up client-side obligations to discharge the liveness invariant required by the specification. Of course, TaDA Live was not conceived in a vacuum. So there's there's Total TaDA, which is the predecessor of TaDA, which only applies to non-blocking code. There's also a large body of work on blocking primitives that are built-in, like built-in locks or channels, but they don't support busy waiting. The closest work to ours is the Lily logic, which proves linearizability by progress-preserving contextual refinement. What they do is prove a module correct with respect to some specification, but there is no client reasoning within the logic and no rule for parallel composition. Additionally, atomic operations may be specified using non-atomic code, which hinders proof scalability. Finally, there's some concurrent independent work that appeared alongside TaDA Live, but is restricted to in the form of busy waiting it can handle, and it has no logical atomicity. There is so much more in the paper. There's the motivation of the design, formalizations, the foolproof system, illustrative example, case studies, and sound argument, and more on related work. And thank you for your attention.
Okay, we don't have a lot of time for questions. There are a couple of questions online. So Adam Chapala asks, how would your example generalize to a case where the shared variable D is repeatedly set and unset for different notifications?
For different notifications, meaning, well, there needs to be some synchronization that says, okay, now the synchronization that happened on D before is done and we can reuse this. So you would need to augment the protocol with this information so that you can regain ownership of the cell, presumably. So the protocol I showed you is very simple, but the expressive power of the Live protocols is very large. You can express very complicated synchronization patterns.
Thanks. So Jesper Bengston says, your predicates now contain information in what seems to be a global state. For local proofs, how much work is required to maintain the knowledge of how the global environment evolves?
So actually, we are doing much better than previous work at that. The idea of obligation, so I showed you the protocols. The protocols only need to collect resources that need to be talked about together. If I had other threads that do not interfere with the protocol I showed, the protocols for the other shared variables could be expressed completely independently of the protocol on the signal. And so we have this focus on resource for protocols that is really making the proof very much thread local. Additionally, these subjective obligations I showed you are really key into keeping the information about the other threads as abstract and local as possible. I don't have time to. I didn't have time to show you the layers, but they are really key in allowing abstractions that tell you, yes, you can rely on this liveness invariant, although you can completely ignore how the environment is going to achieve it. So the logic is actually really thread local in that.
Okay, thank you.